Aligning large language models to a domain-specific graph database for NL2GQL. Yuanyuan Liang 1, Keren Tan 1, Tingyu 2, Wenbiao Tao 1, Siyuan Weining 1, Yunshi Lan 1, Weining 1. 1 East China Normal University, 2 Zhejiang University. Yuanyuan, Keren 1020, Wotao, Saiwang, at stu.ecnu.edu.cn, Tingyu at zu.edu.cn, Islan, Wonqian at days.ecnu.edu.edu.cn. Corresponding author. Abstract. Graph databases, GraphDB, find extensive application across diverse domains such as finance, social networks, and medicine. Yet, the translation of natural language, NL, into the graph query language, GQL, referred to as NL2GQL, poses significant challenges owing to its intricate and specialized nature. Some approaches have sought to utilize large language models, LLMs, to address analogous tasks like text-to-SQL. Nonetheless, in the realm of NL2GQL tasks tailored to a particular domain, the absence of domain-specific NL-GQL data pairs adds complexity to aligning LLMs with the GraphDB. To tackle this challenge, we present a well-defined pipeline. Initially, we utilize ChatGPT to generate NL-GQL data pairs, leveraging the provided GraphDB with self-instruction. Subsequently, we employ the generated data to fine-tune LLMs, ensuring alignment between LLMs and the GraphDB. Moreover, we find the importance of relevant schema in efficiently generating accurate GQLs. Thus, we introduce a method to extract relevant schema as the input context. We evaluate our method using 2 carefully constructed datasets derived from GraphDBs in the finance and medicine domains, named FinGQL and MediGQL. Experimental results reveal that our approach significantly outperforms a set of baseline methods, with improvements of 5.90 and 6.36 absolute points on EM, and 6.00 and 7.09 absolute points on X, for FinGQL and MediGQL, respectively. Aligning large language models to a domain-specific graph database for NL2GQL. Yuanyuan Liang 1, Keren Tan 1, Tingyu 2, Wenbiao Tao 1, Siyuan 1, Yunshi Lan 1, Weining 1. 1 East China Normal University, 2 Zhejiang University. Yuanyuan, Keren 1020, Wotao, Saiwang at stu.icnu.edu.cn. Tingyu at stu.edu.cn, Islan, Wonqian at days.icnu.edu.cn. 1 Introduction. Presently, leading graph databases, GraphDBs, such as Neo4j, Nebula Graph, and Janus Graph are extensively utilized for storing graph data. Wang et al. 2020. Lopes et al. 2023. These GraphDBs have broad applications across various domains, including finance, healthcare, social networks, and e-commerce. However, the nuanced and complex syntax of the graph query language, GQL, presents hurdles for general users endeavoring to convert natural language, NL, into GQL. Figure 1 illustrates a NL2GQL example. A GQL consists of keywords match, where, and return leading the retrieval functions towards a GraphDB. Several factors combine to render NL2GQL an exceedingly challenging task. Primarily, the inherent complexity of NL understanding poses initial hurdles due to its intricate nature. Additionally, the intricate syntax of GQL further compounds the difficulty. Montero et al. 2023. Furthermore, the diversity of terminology and conventions within domain-specific graph data adds another layer of complexity to the translation process. Refer to caption. Figure 1: an instance of the NL2GQL task in the financial domain, which entails the conversion of NL into GQL tailored for a specific GraphDB. While the NL2GQL task is both highly significant and extremely challenging, recent research on this topic is remarkably scarce. The predominant research emphasis is on the conversion of NL into cipher, which is an efficient GQL aligned to the Nebula Graph. Guo et al. 2022. Released a general domain text-to-cipher dataset and explored the application of a basic sec-to-sec framework for this task. Nevertheless, the accuracy of their proposed baseline method is notably low. barely surpassing a meager 2%. Zhou et al. 2023 developed a hybrid approach combining smaller and larger foundation models to improve NL2GQL accuracy in general domain. Considering the connection between NL2GQL and text-to-SQL tasks, Zhou et al. 2024 developed a SQL2 cipher algorithm capable of mapping SQL queries to cipher queries. However, the relationship between schema items relies heavily on the domain knowledge, which cannot be easily generalized from general domain. Above approaches are hard to be applied to NL2GQL over a domain-specific GraphDB. In the last year, large language models, LLMs, have transitioned from emerging technologies to widely used applications. Wei et al. 2022a, Zhao et al. 2023, Kador et al. 2023, Zi et al. 2023. Concurrently, a body of research substantiates the robust capacity of LLMs in transforming NL into logical forms. Luo et al. 2023, Meyer et al. 2023, Li et al. 2023. With a lack of training data, although these methods have achieved certain results, their methods are tailored to knowledge graphs, KGs, which are stored in Resource Description Framework, RDF, PAN, 2009, and have distinct schema structure to GraphDBs. There is still a significant gap for LLMs application in NL2GQL. In order to improve the performance of NL2GQL tasks on a specific GraphDB without any label data, we propose a well-defined pipeline, as depicted in Figure 2. First, we generate NL-GQL pairs as instructions based on a given GraphDB for fine-tuning LLMs. Specifically, starting from the GraphDB, we collect a set of canonical NL-GQL template pairs. Subsequently, we employ a two-step self-instruct Wang et al. 2022 method to extend these initial pairs, generating a comprehensive collection of NL-GQL template pairs, and further being verified via chain of thought, Wei et al. 2022c. This ensures broad query coverage and diverse expressions while maintaining consistency between NL template and GQL template. The resulting NL-GQL template pairs undergo GraphDB grounding to get complete NL-GQL data pairs. Secondly, we align a foundation LLM to the GraphDB with Lo Ra Hu et al. 2021. During inference, we organize the schema that is relevant to NL for prompting the aligned LLMs. We evaluate the performance of our aligned on the GraphDBs in finance and medicine domains. We select traditional fine-tuned methods and in-context learning, ICL, methods as baseline methods. The experimental results demonstrate that our method outperforms all of the baseline methods by a noticeable margin. We summarize our contributions as follows. We introduced a pipeline for aligning LLMs with a domain-specific GraphDB, enabling the seamless incorporation of pertinent information from the graph database and its stored data into LLMs to enhance the accuracy and inference speed of LLM on NL2GQL tasks. We propose a method that extracts a portion of schema from the graph database schema, which is relevant to NL, to serve as input context. Experimental results showcase the superior effectiveness of our proposed approach compared to the baseline. Refer to caption. Figure 2: Overview of our method. 2. Related work. 2.1 NL2GQL. NL2GQL is an emerging task that requires a system to convert a natural language question into formats compatible with GraphDB. The system should have strong capabilities of question understanding and GQL parsing. Initial endeavors focused on direct translations from natural language to queries, primarily relying on handcrafted rules. Zhao et al. 2022. More recent studies shift towards data-driven approaches. By training a sequence-to-sequence model on NL2GQL datasets, a system can learn the transition from NL to GQL well. Guo et al. 2022. Our study demonstrates innovation in solving NL2 over a domain-specific GraphDB and aligning LLMs to such a GraphDB. We also notice that text-to-SQL and KGQA, question answering over knowledge graphs, are analogous tasks to NL2GQL, where the query language are compatible with traditional DBs and knowledge bases, respectively. Even though prior studies have developed a number of text-to-SQL as well as KGQA datasets and end-to-end systems. Gao et al. 2023a. Chang and Fossler Lucier, 2023, Gu et al. 2023, Saxena et al. 2020, Zhang and Uzbek, 2022, they cannot be directly transferred to NL2GQL. NL2GQL proves its differences in complex graph modality, variance query types, and distinct graph query languages. Zhou et al. 2023. While our approach aligns with NL2SQL in terms of the methodological flow, there are substantial disparities in solving NL2GQL over a domain-specific graph DB. 2.2 Fusing LLMs and databases. LLMs have shown its powerful capabilities in a diverse range of NLP tasks. Min et al. 2023, Kador et al. 2023, Ferrara, 2023. Incorporating LLMs with databases is an important research question. Pan et al. 2024, Luo et al. 2023, Gao et al. 2023 B. Pereza and Raffier, 2023, Zhou et al. 2023, which benefits to improve the efficiency of structured data processing and ease the hallucination issues of LLMs. The integration of LLMs and structured DB is primarily approached through two main paradigms. The first paradigm extracts the information from databases to enhance the context for prompting LLMs in generation. For instance, techniques like retrieval augmented generation, RAG, Gao et al. 2023c, can be employed to retrieve and query relevant data from databases, thereby enhancing the generated results. Kang et al. 2023a, Wang et al. 2023, Motoresi et al. 2023, Luo et al. 2023, Yang et al. 2023b, Gu et al. 2023, Zhou et al. 2023 during inference. The second paradigm injects the knowledge of databases into LLMs by fine-tuning Decao et al. 2021, Lin et al. 2021, Sen et al. 2023, Kang et al. 2023b. A key aspect of this approach is to make controllable edit to the parameters in LLMs. Our approach takes advantages of both paradigm. We tuned a foundation LLM to align it to knowledge of a graph DB on the one hand. On the other hand, we elaborately extract relevant schema from the graph DB for prompting, which deeply fuses LLMs and databases together. 3. Preliminary. 3.1 Graph databases. A graph database, G, is a relational database which is stored in the form of G equals S, R, O, S, O, E, I, R, V. Dot here, E, I, V, denotes the vertex set and the edge set respectively. Graph database is a property graph, where every vertex and edge can be defined with labels and have any number of properties, aka attributes. Vesta et al. 2023. Each graph database is associated with a schema. S. 3.2 NL2GQL with LLMs. When it comes a natural language query, Q, inquiring about the information in G, NL2GQL task requires a system to transfer Q into a graph database language query, L. For example, Cipher, NGQL, and Gremlin, which can be executed over G to retrieve the predicted answer. In this paper, we treat an LLM as an NL2GQL system to map Q to L with the consideration of predefined G. For our method, in order to align LLMs to a graph DB and achieve NL2GQL with high accuracy, we propose a pipeline as illustrated in Figure 2. Initially, we generate NL-GQL pairs as instruction for fine-tuning the LLM. Specifically, starting from the graph DB, we collect a set of canonical NL-GQL templates annotated with GQL. Then we extend these seed pairs to a set of NL-GQL pairs with a wide query coverage and diverse expressions via two-step data augmentation based on ChatGPT. These generated NL-GQL pairs are further grounded and verified. Next, we fine-tune LLMs via low RA with the generated instruction such that the tuned LLM will be aligned with the knowledge in the graph DB. For inference, to bound the LLMs with the graph DB schema, We organize the relevant schema to the query as the context of the prompt and request the LLM to produce GQL using the identified schema. 4.1 Generating NL-GQL pairs as instructions. It is non-trivial to construct NL-GQL data pairs deriving from a given G. Different from the majority of existing QA over DB challenges like Spider U et al. 2018, Grail QA Gu et al. 2021, and SPCQL Guo et al. 2022, where the narrative questions are associated with a database in general domain. G is in specific domains such that it is not applicable to employ the above datasets as initialization. In addition, it is impossible to be scaled up if we solely rely on human labor to annotate the NL-GQL pairs in a specific domain. Therefore, it is vital to develop a labor-saving pipeline to generate high-quality NL-GQL pairs that are able to cover a wide range of query types on a specific domain. Therefore, we employ ChatGPT to play an important role in the pipeline of NL-GQL pairs generation, with the awareness that ChatGPT have lack of the specific knowledge of A NL-GQL template collector module is developed to collect the canonical NL-GQL templates, which decouple the redundant schema items from the GQL. Then, a two-step instruction generator with self-instruct module is implemented. Its first step strengthens the guidance to ChatGPT on S via providing the schema of GraphDB as well as canonical NL-GQL templates as context for prompting. In its second step, the outputs are verified via GQL2NL with reasoning the intermediate steps. Furthermore, we continue to improve the quality and coverage of instructions by self-supervising the instruction tuning process until the desired number of NL-GQL pairs is obtained. Eventually, we ground the NL-GQL pairs via a GraphDB grounding module. NL-GQL template collector. To ensure the diversity and comprehensiveness of generated NL-GQL on different GraphDB, we formulate an NL-GQL template as a narrative question with masked schema items, i.e., entities and properties, followed by a GQL skeleton, where the entity labels and properties of the node are masked out. An example is shown below. What is entity S, property? Match S node name, entity. Return S.node, property, where we employ the placeholder entity to denote the named entities and property to denote the property of an entity in both the NL and GQL. We define 8 types of the canonical NL-GQL templates covering queries about entity property, numerical sorting, attribute comparison and so on. 1. For each NL type, we manually annotate K data pairs and include them into a data pool. D. As we can see, the NL-GQL templates are able to decouple the schema-related information for the queries while keeping the main semantics and syntax, which can be adapted to different domains. Schema of GraphDB. Nodes. Tag, stock, properties, code, string, edges. Edge has _stock_data, start_tag_stock, end_tag_stock_data, properties, task description, please generate a new NL-GQL template data pair of the same type as the provided NL, based on the given graph database schema and NL-GQL. Demonstrations. In the NL-GQL, what is entity S.code? Match S.stock name, entity. Return S.stock.code. Table 1. The prompt for NL-GQL data pair generation. Two-step instruction generator with self-instruct. The first step aims to generate candidate NL-GQL pairs with S, as well as D. And using ChatGPT, we design a unified prompt but adjust to the different types of query by changing instructions for each category. As shown in Table 1, each prompt consists of the following components. Schema of GraphDB, according to Gao et al. 2023b, including the DB schema in the prompt helps the generation of SQL that fits the DB. Therefore, our prompt used for generating NL-GQL data pairs consists of the entire schema of the GraphDB. Specifically, we organize the schema by flattening the nodes set into a sequence, wherein each node type is represented as a key accompanied by its corresponding properties. Similarly, each edge is defined with its start and end node types, along with any associated properties, as depicted in Table 1. Task description. It is a textual sequence describing the query type of pairs to be generated. We predefine the description in Appendix C, NL-GQL. We sample K. Examples of a certain type from D, and randomly sample properties from the schema to instantiate the property variable, resulting in different demonstrations. In this case, we can prompt LLMs to generate NL-GQL pairs that are related to the graph DB. For simplicity, we denote this procedure as Q L equals NL-GQL gen S D. The second step takes L as the input and aims to verify NL with GQL generated from the first step. Several studies, Wei et al. 2022, C. Kojima et al. 2022, Zhou et al. 2022, Diao et al. 2023, have established the efficacy of utilizing Ko-T Wei et al. 2022b to yield more accurate answers by generating intermediate reasoning steps. In this step, we apply Ko-T to conduct GQL to NL, the goal of which lies in verifying the quality of the generated NL given a GQL. The prompt format closely resembles that of Table 1, with the task-adjusted description and replacement of NL-GQL with COT-based GQL to NL demonstrations. COT-based GQL to NL. We take the K examples in the first step but present the transition from GQL to NL in the format of an explicit reasoning chain. Specifically, we break down the GQL into individual keywords function clauses based on keywords such as match, where, and return. For example, the given GQL is match s stock name entity return s.stock.code. Its COT process is as follows. Match s stock name entity identifies the entity with the stock name entity. Return s.stock.code returns the code of the stock. Combining these two parts, so the output is, what is entity s code? Therefore, we can obtain an alternative question by prompting LLMs with the given GQL. For simplicity, we denote this procedure as Q equals GQL to NL gen S L dot to ensure the consistency of L and present C Q. Across all data entries, we compare encode them via the sequence matching encoder and compare their similarities. If it falls below a certain threshold, we consider the Q and L to be inconsistent, leading to the discarding of the respective data entry. Otherwise, we include the NL-GQL pairs into data pool. Q L D dot. The two-step generation results in high-quality NL-GQL pairs. To enhance the diversity of NL-GQL pairs, we conduct self-instruct Wang et al. 2022 for the generation procedure, where the demonstrations used for the next iteration are extracted from D. This iterative process continues until we generate enough NL-GQL pairs. Graph DB grounding. In the previous steps, all generated NL and GQL pairs in D are templates with entity placeholders. Then, we replace these placeholders with named entities from the graph DB to obtain instantiation of NL as well as GQL. The GQLs are executed over the associated graph DB to check if they are semantically and syntactically correct to retrieve the answers. Only the executable NL-GQL pairs will saved. As a result, we have a high-quality data pool in specific domain with each entry containing an NL-GQL, template NL, template GQL, and the corresponding executed answers. 4.2 Aligning LLMs to a graph DB with low RA. After we generate a set of NL-GQL pairs, we can fine-tune an existing foundation LLM to align with the graph DB. To avoid extensive parameter tuning, we apply parameter-efficient fine-tuning, PEFT, techniques, which is able to minimize fine-tuning parameters and optimize memory usage while maintaining the performance. Liu et al. 2022. Hu et al. 2021. We choose Lo Ra Hu et al. 2021 for fine-tuning the selected LLMs due to its wide application. Specifically, we feed the NL-GQL pairs obtained from section 4.1 into the LLMs. For each pair, we extract the schema items in the GQL as the context to the NL as an instruction, then supervised fine-tuning calculates the cross-entropy loss over the ground truth GQL. In this way, the fine-tuned LLMs learn the schema of the domain-specific graph DB and understand the transition from the NL to the GQL. 4.3 Organizing schema for prompting. Regarding inference for NL2GQL tasks, we prompt the tuned LLM to generate L given Q directly. Similar attempts have been carried on text-to-SQL by representing a DB schema with a linear code sequence and appending the sequence as the context for prompting Nan et al. 2023. We prepend the schema of the graph DB as context, but differ in the way of formulation. Specifically, we extract the key schema items that are relevant to the NL rather than the entire schema as the context. To this end, a label linker is used to extract the named entities from Q and link them to the labels in the graph DB. Then, a LLM prompt organizes the extracted labels as the context and generates the main body of the GQL. Eventually, a join table linker further infers the joint tables based on the extracted labels and append it to the main body to form a prompt. Label linker. To accurately identify named entities in NL and link them to the labels in the graph DB, we first collect all the labels from the graph DB and store them in a dictionary, where the labels are saved as the key, and their corresponding properties are saved as the value. When there comes a and Q. We tokenize the sentence and employ an off-the-shelf named entity tagger to identify the named entities within it. Then, we map these named entities to possible keys in the dictionary by a string match. This step may result in multiple ambiguous labels. For example, the named entity Sam could be linked to either a fund manager or a chairman. We disambiguate the named entities by choosing the labels in a GQL from D, the NL of which has the highest similarity to Q. Join table linker. Since many questions inquire about information that requires reasoning across multiple tables, but not all table information is explicitly mentioned in the question, it is necessary to perform table linking with the linked labels. We formulate the problem as searching for the shortest path through the tables where the identified labels are located. We utilize the A algorithm Hart et al. 1968 to address the shortest path problem. This results in the shortest chain linking all the identified labels, which serves as the match keyword function in a GQL. Relevant schema of graph DB. Nodes. Tag, stock, properties, code, string, edges. Edge has underscore stock underscore data, start underscore tag apostrophe colon stock. End underscore tag apostrophe colon stock underscore data, properties, task description. You are a graph database expert. Please write the corresponding graph query language-based on the relevant schema and natural language, NL, which stocks have a minimum price below 20 and an opening price below 30 today? Table 2, the prompt for fine-tuning LLMs. The match keyword function of inferred GQL is verified by the outputs of joint table linker to form an executable GQL. LLM prompt. After acquiring the relevant schema, incorporate the task description and input natural language to compose a comprehensive prompt, as shown in Table 2. 5 experiments. 5.1 Experimental setup. Datasets FinGQL MediGQL. Train dev test. Graph DB info. Hashtag nodes. 668,508. /12. Type spots 44,656. /8. Types. Hashtag edges. 730,583. /14. Types 312,159. /12. Types. Hashtag properties. 62. Types 14. Types. Dataset info. Hashtag nodes, average. 1.81. 1.78, 1.81, 1.76, 1.84, 1.73. Hashtag edge, average. 0.81, 0.78, 0.81, 0.86, 0.90, 0.83. Hashtag unique template. 1434, 229, 419, 1907, 293, 590. Hashtag NL-GQL. 7,000, 1,000, 2,000, 6,000, 850, 1,700. Table 3. Statistics of the generated datasets. Evaluation set construction. To verify the way we fine-tune a foundation LLM and prompt the tuned LLM for solving NL2GQL over a domain-specific graph DB, we choose stock G2 and disease G3 as the graph DB in finance and medicine domains, respectively. We follow the pipeline description in section 4.1 to generate a number of NL-GQL pairs. We randomly partitioned the data pool into training, development, and test sets with ratios of 7:1:2, respectively. The correctness of test sets are further verified manually. These two datasets, namely FinGQL and MediGQL, have statistics shown in Table 3 and can be leveraged to support future research on NL2GQL over domain-specific graph DB4. We will release the datasets upon acceptance. Method backbones FinGQL MediGQL. EMX. Fine-tuning MBART large 69.55 53.45 64.92 54.56. MT5 large 73.75 67.75 79.69 65.04. In-context learning Baichuan 213b chat 18.20 14.9 023.54 18.24. Chatglam 36b 16.10 17.75 18.78 16.13. Quen 14b chat 21.10 22.75 24.24 21.07. ChatGPT 3.540.6540.10 49.38 41.38. Rs Baichuan 213b chat 78.10 71.25 84.54 71.38. Chatglam 36b 77.30 68.95 83.8 170.51. Quen 14b chat 79.65 73.75 86.05 72.13. Table 4. Comparison between our method and the baseline method. The bold numbers indicate the best results. Evaluation metrics. We follow the evaluation methods of text-to-SQL, which include exact set match accuracy, EM, and execution accuracy, X, Yu et al., 2018. EM measures the consistency of the individual components split by keywords within the predicted query and its corresponding ground truth, whereas X compares whether the execution results on the database are consistent between the two. Baseline methods. To validate and compare the effectiveness of our method, we selected two categories of methods as baselines. Fine-tuning methods. Instead of constructing instructions for fine-tuning, we employ the traditional approach Liu et al., 2022, Guo et al., 2022, to fine-tune a pre-trained model, where the NL from NL-GQL data pairs serves as input, and the GQL serves as the label for training, in-context learning methods. We follow the RAG paradigm to include the schema of GraphDB as the context and sample. K. Examples with large semantic similarities to the NL as the demonstrations for prompting LLMs during inference, Dong et al., 2023, Gao et al., 2024. Implementation details. In selecting the backbone LLMs, we prioritize LLMs compatible with both Chinese and English due to the language of employed GraphDB. As a result, we choose Baichuan 213b chat Yang et al., 2023a, Chatglam 36b Zheng et al., 2022, and Quen 14b chat Bei et al., 2023, as the foundation LLMs to be aligned. Regarding fine-tuning methods, We select MBART Large Tang et al. 2020 and MT5 Large Shui et al. 2021 as the pre-trained models due to their wide application in multilingual scenarios. Regarding the sequence matching for demonstration selection, we utilized the All-Mini LML6v2 checkpoint from the Sentence Transformers library to encode a sequence. The threshold for verifying the NLs from 2 steps in NL-GQL pair generation is set as 0.8. All the number of demonstrations K are set as 8. Our experiments were implemented on an A800 GPU. 5.2 Main results. Table 4 illustrates a performance comparison between our method and the baseline methods. From the experimental results, we can draw the following conclusions. A. Our approach demonstrates a significant improvement over the best baseline methods. Specifically, on the FinGQL dataset, it outperforms them by 5.90% on the EM metric and by 6.00% on the X metric. Similarly, on the MediGQL dataset, it surpasses them by 6.36% on the EM metric and by 7.09% on the X metric. B. Backbone model is crucial for the NL2GQL task. The MT5 large model consistently outperforms the MBART large model. Additionally, both the ICL method and our approach demonstrate that the Qwen14B chat model yields significantly better results compared to other open-source LLMs. Furthermore, within the ICL method, ChatGPT 3.5 exhibits notably superior performance compared to several other LLMs, although it only achieves roughly half the accuracy of our approach. C. It's evident that a simplistic ICL method isn't suitable for NL2GQL. This may be attributed to the lack of domain knowledge from the data within the GraphDB. To improve the effectiveness of the ICL method, further research is needed in prompt design to better guide LLMs in extracting domain knowledge. Furthermore, it is evident from the result table that EM values generally exceed those of X. EM serves as a more forgiving evaluation metric, while X provides a more precise assessment by directly comparing GQL execution outcomes. 5.3 Comparison with domain-specific LLMs. One of the reasons why the ICL performs poorly on the NL2GQL task is its insufficient understanding of the domain-specific knowledge. Therefore, we are interested in exploring whether domain-specific LLMs can perform better. We experiment on 2 well-known medical domain LLMs, Huatuog P27B Chen et al. 2023a and Bian K2 Chen et al. 2023b, and the results are in Table 5. As shown in the table, compared to the general domain ChatGLM36b and Qwen14b chat, the domain-specific Huatuog P27b and Bian K2 LLMs perform very poorly. It is presumably because they focus too much on domain-specific knowledge and tasks, neglecting general knowledge and tasks. During the domain-specific supervised fine-tuning, the ability of language conversion of LLMs is largely compromised, resulting in poor performance in the NL2GQL task. Domain model EMX. Medical domain Huatuog P27B0.059.0.059. Beyond K20.180.18. General domain ChatGLM 36B16.1017.75. Qwen14B chat 21.1022.75. Table 5. The comparison of performance between medical domain LLMs and general domain LLMs using the ICL method on the MediGQL dataset. 5.4 Further analysis. Efficiency analysis. To observe the inference speed of our method, we conducted experiments on the test set of FinGQL and recorded its execution time. The results are shown in Table 6. Based on Table 6 and Table 8, it is evident that our strategy of incorporating the relevant Chinese schema leads to a substantial enhancement in effectiveness, accompanied by a slight increase in inference time. However, adding the full schema will significantly increase the inference time, and including unrelated distracting information may also lead to a decrease in accuracy. Method execute time, sec. Without schema 0.777. Full schema 1.32. Full Chinese schema 1.52. Relevant schema 0.87. Relevant Chinese schema, hours, 0.88. Table 6. Comparison of average inference times for various schema-related methods on the FinGQL dataset, measured in seconds. Breakdown analysis. For a more detailed analysis of our method's performance across various query types, we segmented the execution results by query type and tabulated the statistics, as presented in Table 7. From the table, it can be observed that the accuracy is relatively low for queries of yes/no question type, edge property type, and attribute comparison type. These three types of queries all involve complex computational problems, so there may be some challenges in generating GQL with accurate calculation logic. Query type EMX. Entity property 81.8, 780.63. Numerical sorting 84.88, 84.88. Relationship inference 84.18, 84.48. Yes/no question 69.40, 68.87. Relationship filtering 79.55, 77.27. Attribute comparison 76.0, 178.50. Edge property 70.15, 71.61. String filtering 88.89, 85.19. Total 79.65, 73.75. Table 7. Performance of our method on various types of queries in the FinGQL dataset. 5.5 Ablation Study. We conducted an ablation study to evaluate the effectiveness of components within our method, and the results are presented in Table 8. The results indicate that removing the Chinese explanations of fields in the schema leads to a deterioration in performance, suggesting their contribution to addressing the Chinese NL2GQL task. Moreover, without any schema leads to a more significant performance drop, highlighting the beneficial role of schema as context in addressing the NL2GQL task. Method EMX. Relevant Chinese schema, hours, 86.05, 72.13. Relevant schema 85.12. 0.9, 71.81. 0.3 without schema 83.46. 2.6, 69.92. 2.2 full schema 85.29. 0.8, 71.98. 0.1 full Chinese schema 85.55. 0.5, 71.34. 0.8 Table 8. Ablation study of our method on MediGQL. The green downward arrow denotes a decrease, and the green number in parentheses indicates the precise decrease value. 6 Conclusion. In this paper, we present a pipeline for addressing the NL2GQL task on a given graph DB. Firstly, we construct an NL2GQL dataset based on the graph database. Then, we fine-tune LLMs using the constructed dataset to align LLMs with the graph database. Additionally, to further enhance the NL2GQL capability of LLMs, we propose a method that extracts schema relevant to NL as input context to guide LLM. Experimental results demonstrate that our approach significantly outperforms baseline methods. Limitations. Although our work is intended to be language agnostic, it is regrettable that our experiments currently only involve Chinese data, as we only have access to domain graph data available in Chinese. References. Bei et al. 2023 Jins Bei, Shuai Bei, Yunfei Chu, Ziyu Kui, Kai Deng, Xiaodong Deng, Yang Fan, Wenbin Ge, Yuhan, Fei Huang, et al. 2023. Quinn Technical Report.R14 Preprint R14-2309.16609. Besta et al. 2023 Mache Besta, Robert Gerstenberger, Emmanuel Peter, Mark Fisher, Michal Podstowski, Claude Barthels, Gustavo Alonso, and Torsten Hoffler. 2023. Demystifying Graph Databases, Analysis and Taxonomy of Data Organization, System Designs, and Graph Queries. ACM Computing Surveys, 56-2, 1-40. Chang and Fossler-Lucier, 2023 Shuhaiken Chang and Eric Fossler-Lucier. 2023. How to Prompt LLMs for Text to SQL, a Study in Zero-Shot, single domain, and cross-domain settings. R14 preprint, R14:2305.11853. Shen et al. 2023 A Junying Shen, Shtong Wang, Aninjie Gao, Feng Zhang, Shunyan Chen, Hongbo Zhang, Dinjia Song, Wenye Shi, Shui Kong, Jiangquan Li, Xiangwan, Heizhou Li, and Benyu Wang. 2023 A. Watuog Pept 2, One-Stage Training for Medical Adaption of LLMs. Shen et al. 2023 B. Yirong Chen, Zhenyu Wang, Xiaofan Xing, Huiman Zheng, Zai-Pei Xu, Kai Feng, Junhong Wang, Xihong Li, Jialing Wu, Qi Lu, and Shengmin Xu. 2023 B. Bianc, Balancing the Questioning and Suggestionability of Health LLMs, with multi-turn health conversations polished by ChatGPT. Decau et al. 2021 Nicola Decau, Wilker Aziz, and Ivan Titov. 2021. Editing Factual Knowledge in Language Models. In Proceedings of the 2021 Conference on Empirical Methods in Natural Language Processing, pages 6491 to 6506, online and Punta Cana, Dominican Republic. Association for Computational Linguistics. Diao et al. 2023 Shizhe Diao, Peng Chung Wang, Yang Lin, and Tong Zheng. 2023. Active Prompting with Chain of Thought for Large Language Models. R14 preprint R14:2302.12246. Dong et al. 2023 Guangshu Dong, Lei Li, Damai Dai, Zhejiang, Jiang Wu, Baobao Cheng, Xu Sun, Jingjing Xu, Lei Li, and Tifang Sui. 2023. A Survey on In-Context Learning. Ferrara, 2023 Emilio Ferrara. 2023. Should ChatGPT be biased? Challenges and Risks of Bias in Large Language Models. R14 preprint R14:2304.03738. Gao et al. 2023 A. Dawei Gao, Haiben Wang, Yale-Yang Li, Shuyu Sun, Yichen Qian, Bolin Ding, and Jingren Zhou. 2023 A. Text-to-SQL Empowered by Large Language Models, a Benchmark Evaluation. R14 preprint R14:2308.15363. Gao et al. 2023 B. Dawei Gao, Haiben Wang, Yale-Yang Li, Shuyu Sun, Yichen Qian, Bolin Ding, and Jingren Zhou. 2023 B. Text-to-SQL Empowered by Large Language Models, a Benchmark Evaluation. Gao et al. 2024 Yunfan Gao, Yunxiang, Xinu Gao, Kangsheng Jia, Jinyu Pan, Yuxi Bai, Yu Dai, Jiawei Sun, Qianu Guo, Meng Wang, and Haofun Wang. 2024. Retrieval Augmented Generation for Large Language Models, a Survey. Gao et al. 2023 See Yunfan Gao, Yunxiang, Xinu Gao, Kangsheng Jia, Jinyu Pan, Yuxi Bai, Yi Dai, Jiawei Sun, and Haofun Wang. 2023 C. Retrieval Augmented Generation for Large Language Models, a Survey. R14 preprint R14:2312.10997. Gu et al. 2021 Yu Gu, Sucase, Michelle Vani, Brian Sadler, Percy Liang, Shifang Yan, and Yusu. 2021. Beyond EAD. 3 Levels of Generalization for Question Answering on Knowledge Bases. In Proceedings of the Web Conference 2021, pages 3477 to 3488. Gu et al. 2023 Ziwei Gu, Zhu Fan, Nan Tang, Lei Cao, Bowen Jia, Sam Madden, and Xiaoyang Du. 2023. Few-shot text-to-SQL translation using structure and content prompt learning. Proceedings of the ACM on Management of Data 1-1-28. Guo et al. 2022 Aibo Guo, Xinyi Li, Guangkan Xiao, Zhen Tan, and Xiang Chao. 2022. SPCQL, a semantic parsing dataset for converting natural language into cipher. In Proceedings of the 31st ACM International Conference on Information and Knowledge Management, pages 3973 to 3977. Hart et al. 1968 Peter E. Hart, Niels J. Nielsen, and Bertram Raphael. 1968. A formal basis for the heuristic determination of minimum cost paths. IEEE transactions on system science and cybernetics, 42, 100-107. Hu et al. 2021 Edward J. Hu, Yilong Shen, Philip Wallace, Zhejiang Alan Zhu, Yuanxi Li, Xin Wang, Lu Wang, and Wizhu Chen. 2021. Laura. Low-rank adaptation of large language models. R14 preprint R14:2106.09685. Zhang and Uzbek. 2022 Longquan Zhang and Ricardo Uzbek. 2022. Knowledge graph question answering datasets and their generalizability. Are they enough for future research? In proceedings of the 45th International ACM SIGR Conference on Research and Development in Information Retrieval, SIGR 22, page 3209-3218, New York, USA. Association for Computing Machinery. Kador et al. 2023 Jean Kador, Joshua Harris, Maximilian Moses, Herbie Bradley, Roberta Raylinu, and Robert McCarty. 2023. Challenges and applications of large language models. R14 preprint R14:2307.10169. Kang et al. 2023 Aminki Kang, Jin Myung Kwok, Jinhyun Baek, and Sung-Ju Huang. 2023 A. Knowledge Graph Augmented Language Models for Knowledge-Grounded Dialogue Generation. R14 preprint R14:2305.18846. Kang et al. 2023 B. Minki Kang, Jin Myung Kwok, Jinhyun Baek, and Sung-Ju Huang. 2023 B. Knowledge Graph Augmented Language Models for Knowledge-Grounded Dialogue Generation. Kojima et al. 2022 Takeshi Kojima, Shisheng Gu, Michelle Reed, Yutaka Matsuo, and Yusuke Iwasawa. 2022. Large language models are zero-shot reasoners. Advances in neural information processing systems. 35 to 22,199 to 22,213. Li et al. 2023 Zhenyu Li, Sunki Fan, Yu Gu, Shuxing Li, Jichao Duan, Bowen Dong, Ning Lu, and Zhenyang Wang. 2023. Flexbedka, a flexible LLM-powered framework for few-shot knowledge base, question answering. R14 preprint, R14:2308.12060. Lin et al. 2021 Weijie Lin, Bo Sheng Seng, and Bill Byrne. 2021. Knowledge-aware graph enhanced GPT-2 for dialogue state tracking. In proceedings of the 2021 Conference on Empirical Methods in Natural Language Processing, pages 7871 to 7881, online and Punta Cana, Dominican Republic. Association for Computational Linguistics. Liu et al. 2022 Hokun Liu, Derek Tam, Mohammed Makayath, Jay Moda, Tinggao Huang, Mohit Bansal, and Colin A. Rafal. 2022. Few-shot parameter efficient fine-tuning is better and cheaper than in-context learning. Advances in neural information processing systems. 35 1950 to 1965. Lopes et al. 2023 Andre Lopes, Diogo Rodriguez, João Saraiva, Mariam Abbasi, Pedro Martins, and Christina Wanseler. 2023. Scalability and performance evaluation of graph database systems. A comparative study of Neo4j, Janus Graph, MumGraph, Nebula Graph, and Tiger Graph in 2023 Second International Conference on Smart Technologies for Smart Nation, Smart TechCon, pages 537 to 542. IEEE. Liu et al. 2022 Yao Jia Liu, Qing Liu, Dai Dai, Shinin Xiao, Honggu Lin, Shanpei Han, Lasun, and Hua Wu. 2022. Unified Structure Generation for Universal Information Extraction. In proceedings of the 60th Annual Meeting of the Association for Computational Linguistics, Volume 1, Long Papers, pages 5755 to 5772, Dublin, Ireland. Association for Computational Linguistics. Luo et al. 2023 Haoren Luo, Zikan Tang, Xiao Peng, Yikai Guo, Wentai Zhang, Chenghao Ma, Guanting Dong, Mina Song, Wei Lin, et al. 2023. ChatGPT, a generate then retrieve framework for knowledge-based question answering with fine-tuned large language models. R14 preprint, R14:2310.08975. Meyer et al. 2023 Lars Peter Meyer, Klaus Stadler, Johannes Frey, Norman Radke, Kurt Junghans, Roy Meissner, Gordian Giwis, Kirill Bullert, and Michael Martin. 2023. LLM Assisted Knowledge Graph Engineering. Experiments with ChatDB.R14 preprint, R14:2307.06917. Minute et al. 2023 Bonin Min, Haley Ross, Elior Sulam, Amir Paran Ben Vaye, Tien Hu Win, Oscar Sines, Eneko Ajir, Ilana Haints, and Dan Roth. 2023. Recent advances in natural language processing via large pre-trained language models. A survey. ACM Computing Surveys, 56-2, 1-40. Modaresi et al. 2023 Ali Modaresi, Ayub Amani, Mohsin Fayez, and Hinrich Schutze. 2023. RET LLM. Towards a general read-write memory for large language models. R14 preprint, R14:2305.14322. Montero et al. 2023 Jessica Montero, Philippe Sa, and Jorge Bernardino. 2023. Experimental evaluation of graph databases, JanusGraph, NebulaGraph, Neo4j, and TigerGraph. Applied Sciences, 13-9, 5770. Nan et al. 2023 Linyang Nan, Yilun Zhao, Wijin Zhou, Narutatsu Ri, Jai Sung Tae, Ellen Zhang, Armin Cohen, and Dragomir Radev. 2023. Enhancing text to SQL capabilities of large language models. A study on prompt design strategies. In the 2023 Conference on Empirical Methods in Natural Language Processing. Pan, 2009 Jeff C. Pan. 2009. Resource Description Framework. In Handbook on Ontologies, pages 71-90, Springer, Pan et al. 2024 Shiroi Pan, Linhao Luo, Yufei Wang, Chen Chen, Jiapu Wang, and Xindong Wu. 2024. Unifying Large Language Models and Knowledge Graphs. A Roadmap. IEEE Transactions on Knowledge and Data Engineering. Peressa and Raffier. 2023 Mohammadreza Peressa and Dawood Raffier. 2023. DIN SQL. Decomposed in-context learning of text to SQL with self-correction. Saxena et al. 2020 Apoorve Saxena, Aditya Tripathi, and Partha Talukdar. 2020. Improving multi-hop question answering over knowledge graphs, using knowledge base embeddings. In Proceedings of the 58th Annual Meeting of the Association for Computational Linguistics, pages 4498-4507, online. Association for Computational Linguistics, Sen et al. 2023 Priyanka Sen, Sandeep Mavadia, and Amir Safari. 2023. Knowledge Graph Augmented Language Models for Complex Question Answering. In Proceedings of the First Workshop on Natural Language Reasoning and Structured Explanations, NLRS, Tang et al. 2020 Yuqing Tang, Chao Tran, Shen Li, Peng Zhenchen, Naman Goyal, Vishrav Chaudhry, Jiao Gu, and Angela Fan. 2020. Multilingual Translation with Extensible Multilingual Pre-Training and Fine-Tuning. Wang et al. 2020 Ran Wang, Zhengyi Yang, Wenji Zhang, and Zuman Lin. 2020. An empirical study on recent graph database systems. In Knowledge Science, Engineering and Management, 13th International Conference, CM 2020, Hangzhou, China, August 28th to 30th, 2020, Proceedings Part 113, pages 328-340, Springer, Wang et al. 2023 Zhentao Wang, Qianwan Yang, Yangting Chu, Jiaqing Liang, Qianu He, Zhouhang Gu, Yanghua Xiao, and Wei Weng. 2023. Knowledged. Enhancing Large Language Models with Retrieval and Storage Access on Knowledge Bases. R14 preprint, R14:2308.11761. Wang et al. 2022 Yizhong Wang, Yagana Kordi, Swarup Mishra, Elisa Liu, Noah A. Smith, Daniel Kashabi, and Hanana Hajisharitsi. 2022. Self-instruct. Aligning language model with self-generated instructions. R14 preprint, R14:2212.10560. Wei et al. 2022 Jason Wei, Yi Tae, Rishi Bamasani, Colin Raffel, Barrett Zoff, Sebastian Bourgeaud, Danny Yogatama, Martin Bosma, Denny Zhou, Donald Metzler, et al. 2022 A.Emergent Abilities of Large Language Models. R14 Preprint, R14:2206.07682. Wei et al. 2022 B. Jason Wei, Zuezi Wang, Dale Shermans, Martin Bosma, Brian Eider, Fei Xia, Ed Chi, Kwok Vila, and Denny Zhou. 2022 B. Chain of Thought, Prompting Elicits Reasoning in Large Language Models. In Advances in Neural Information Processing Systems, Volume 35, pages 24,824 to 24,837. Keren Associates Incorporated. Wei et al. 2022 C. Jason Wei, Zuezi Wang, Dale Shermans, Martin Bosma, Fei Xia, Ed Chi, Kwok Vila, Denny Zhou, et al. 2022 C. Chain of Thought, Prompting Elicits Reasoning in Large Language Models. Advances in Neural Information Processing Systems, 35 to 24,824 to 24,837. C. et al. 2023 Ji Hengxi, Wensheng Chen, Xin Guo, Wei He, Yuan Ding, Boyang Heng, Ming Zhang, Junjie Wang, Senji Jin, NU Zhou, et al. 2023. The Rise and Potential of Large Language Model-Based Agents. A Survey. R14 Preprint R14:2309.07864. Shui et al. 2021 Linting Shui, Noah Constant, Adam Roberts, Mir Kale, Ramial Rafu, Aditya Siddhant, Aditya Barua, and Colin Raffel. On Antilingual Pre-Trained Text-to-Text-to-Text Transformer. In Proceedings of the 2021 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, pages 483 to 498, online. Association for Computational Linguistics, Yang et al., 2023 A. Yuanyuan, Bin Xiao, Bingning Wang, Barong Zhang, Sei Bian, Zhao Yin, Chengshu Lv, Dipan, Diane Wang, Dong Yen, et al. 2023 A. Baichuan 2. Open Large-Scale Language Models. R14 Preprint R14:2309.10305. Yang et al. 2023 B. Suangtao Yang, Mao Tang, Xiaosheng Dong, and Fu Bo. 2023 B. LLM-based Sparkle Generation with Selected Schema from Large-Scale Knowledge Base. In China Conference on Knowledge Graph and Semantic Computing, pages 304 to 316, Springer. Yu et al., 2018 Tao Yu, Rui Zhang, Kai Yang, Michihiro Yasunaga, Dongshu Wang, Zifan Li, James Ma, Irene Li, Conning Yao, Chanel Roman, et al., 2018. Spider. A large-scale human-labeled dataset for complex and cross-domain semantic parsing and text-to-SQL task. R14, Preprint R14:1809.08887. Zheng et al. 2022 Aoan Zheng, Xiaolu, Zhangxiao Du, Zihan Wang, Hanyu Lai, Ming Ding, Zoyi Yang, Yifan Shu, Wendy Zheng, Xiao Xia, et al. 2022. GLM 130B. An open bilingual pre-trained model. R14 Preprint R14:2210.02414. Zhao et al. 2023 Wayne Xin Zhao, Kun Zhou, Junyi Li, Tianyi Tang, Xiaolei Wang, Yupeng Ho, Yinqian Min, Beichen Zhang, Junji Zhang, Zikan Dong, et al. 2023. A Survey of Large Language Models. R14 Preprint R14:2303.18223. Zhao et al. 2024 Ziyu Zhao, Wei Lu, Tim French, and Michael Stewart. 2024. Spider. A neural semantic parsing corpus with baseline models for property graphs. In AI 2023. Advances in Artificial Intelligence, pages 120 to 132, Singapore. Springer Nature Singapore. Zhao et al. 2022 Ziyu Zhao, Michael Stewart, Wei Lu, Tim French, and Melinda Hodkiewicz. 2022. Natural Language Query for Technical Knowledge Graph Navigation. In Australasian Conference on Data Mining, pages 176 to 191, Springer. Zhou et al. 2022, Denny Zhou, Nathaniel Scarley, Laho, Jason Wei, Nathan Scales, Zuezi Wang, Dale Shermans, Claire Cui, Olivier Busque, Kwok Le, et al. 2022. Least to most prompting enables complex reasoning in large language models. R14 preprint, R14:2205.10625. Zhou et al., 2023. Yuhang He Yu, Siyuan, Dan Chen, Liujia Zhou, Zhenlin Yu, Chuanjin Ji, Sen Lu, Guangnan Ye, and Hongfeng Chai. 2023. R3. NL2GQL. A hybrid models approach for accuracy enhancing and hallucinations mitigation. Appendix: a query type. Based on the logical structure between nodes, edges, and properties that may be involved in queries, we summarized the queries and classified them into 8 query types, which are presented in Table 10. Appendix: B dataset presentation. The FinGQL dataset comprises a total of 10,000 records, each consisting of an NL along with its corresponding GQL, a template NL along with its corresponding template GQL, the corresponding GQL answer, and the query type ID. Furthermore, nodes and edges are extracted from the GQL to provide relevant schema during training. Similarly, the MediGQL dataset consists of 8,550 records. An example from the FinGQL dataset is as follows. NL CJKUTF8GBSN 1. In the steel industry, which stocks have opening prices greater than 1, GQL? Match T trade name, CJKUTF8GBSN, steel, less than BT belong _2, S stock, HSD has _stock _data, greater than SD stock _data, where SD.stock _data. Opening _price, greater than 1 return S.stock.name. Template NL. CJKUTF8GBSN, TM. In the T industry, which stocks have opening prices greater than M, template GQL. Match T trade name, T, less than BT belong _2, S stock, HSD, has _stock _data, greater than SD stock _data, where SD.stock _data. Opening _price, greater than M return S.stock.name. Query type ID. 6. Nodes. Stock _data, edges, has _stock _data, belong to appendix NL-GQL data pairs generation task description. We aim to guide ChatGPT in generating NL-GQL template data pairs of the desired query type. Merely including schema and demonstrations in the prompt is not sufficient. Detailed descriptions of the desired query types and explanations of the specific constraints associated with each type are also necessary. Our task description follows the format below. Please generate a new NL-GQL template data pair of the same type as the provided NL based on the given graph database schema and NL-GQL demonstrations. In the graph database schema section, nodes contain information about all entities, including node tags and their corresponding properties. Edges contain information about all relationships, including the head and tail nodes of the edge and any edge properties. In the NL-GQL demonstrations, named entities are replaced with placeholders. For example, stock is represented by S, chairman by C, trade by T. Description of all replacement characters for nodes and edges in the schema is provided below. Due to space constraints, only a portion is written. The query type is query type. In this type, query type description. In the above task description, replace query type and its corresponding query type description with the type of NL to be generated. The query type descriptions we summarized are shown in Table 11. Appendix Ablation Study on FinGQL. We present Table 9 to showcase ablation studies on FinGQL datasets. Additionally, we recognize the importance of relevant Chinese schema in assisting LLMs to generate more accurate GQL. It is worth noting that we did not conduct experiments with the full schema approach due to the 2048 input length limit of Qwen 14 bchat. Adding the full schema would exceed this limit. This underscores the importance of the strategy to extract the relevant schema of NL in our method. Method EMX. Relevant Chinese schema 79.6573.75. Relevant schema 77.85. 1.8, 71.85. 1.9 without schema 77.35. 2.3, 71.55. 2.2 Table 9. Oblation study of our method on FinGQL. The green downward arrow denotes a decrease, and the green number in parentheses indicates the precise decrease value. Query type number 1 entity property, type number 2 numerical sorting. NL template. What is entity S property? The property 2 of node with the highest. Property 1. GQL template. Match S node name. Entity return S dot node. Property. Match S node with S dot node. Property 2, A as N1. S dot node. Property 1, A as N2 order by N2DESC. Limit 1 return N1. Query type number 3 relationship inference, type number 4 yes/no question. NL template. The property of node 1 rel 2 by entity is the property of the entity greater than mount. GQL template. Match S1 colon node 1 less than dash rel 1 S2 colon node 2 less than dash rel 2 S3 colon node 3 name entity return S1 dot node 1 property. Match S node name entity return S dot node property greater than mount. Query type number 5 relationship filtering, type number 6 attribute comparison. NL template. The property of node 2 that rel entity 1 and entity 2. How much does the property of entity 1 differ from that of entity 2? GQL template. Match S1 colon node 1 name entity 1 less than dash rel dash S2 colon node 2 dash rel greater than S3 colon node 1 name entity 2 return S2 colon node 2. Match S1 colon node name entity 1 with S1 dot node property AST1. Match S2 colon node name entity 2 with ABS S2 dot node property T1 as abs underscore diff return abs underscore diff. Query type number 7 edge property, type number 8 string filtering. NL template. The property of node 2 that rel entity with R underscore property less than M. The property of the node containing the string. GQL template. Match S1 colon node 1 name entity R rel dash greater than S2 colon node 2 where R underscore property less than M return S2 dot node 2 property. Match S node where S dot node property contains string return S dot node property. Table 10 to 8 canonical query types along with their corresponding NL and GQL templates. Query type descriptions. Type number 1 entity property. The generated NL and GQL are both related to simple property queries of nodes and do not involve any computations. Type number 2 numerical sorting. The generated NL and GQL are both related to sorting concepts and numerical values. Type number 3 relationship inference. The generated NL and GQL are both related to reasoning about relationships between nodes and edges. Type number 4 yes/no question. The generated NL and GQL both pertain to weather or existence-related queries. Type number 5 relationship filtering. The generated NL and GQL are both related to filtering relationships on multi-hop subgraphs associated with nodes. Type number 6 attribute comparison. The generated NL and GQL are both related to aggregate calculations of node properties. Type number 7 edge property. The generated NL and GQL are both related to comparing and aggregating calculations of edge properties. Type number 8 string filtering. The generated NL and GQL are both related to string matching